Okay, let's state the theorem again. So the theorem we want to prove is the following. So as usual, we have H. And the theorem is, we want to get an if and only if condition for a Gaussian state. We have noticed that, I mean, it's just an observation that any Gaussian state is actually given by a mean and a covariance matrix. And we have also observed that we can get, if the covariance matrix is fixed, then we can get any Gaussian state, we can get a Gaussian state with whatever the mean we want. Okay? We can get all vectors as mean of a Gaussian vector. Okay. So we will consider the if and only if statement for the necessary and sufficient condition for a characteristic function to be a characteristic a function to be a characteristic function of a Gaussian state in terms of covariance matrix with zero mean. Okay. So let me state the theorem. So let f from Cn to C, okay, defined by, and S is in M2n, or it's a real R2n cross R2n matrix, okay, given by f of z equal to exponential.
Sir.
Yeah.
Like we can't see what you're writing.
You don't see? Oh. Okay. It is taking time. Maybe we'll collect through the cable.
Yeah.
Okay. Okay, so f of z equal to, so the mean is 0. We only have the covariance matrix half. So this is a real matrix, so we want to write it xy sxy, okay, where z is equal to x plus iy. Okay, is a characteristic function of a Gaussian state if and only if. So let me write it first. Ij is greater than or equal to 0. That is inner product of xy s minus ij xy is greater than or equal to 0 for all xy in all 2n, which is equivalent to saying, so this, since this is not looking very nice, I prefer to write it this way. Okay? That s minus ij hat is greater than 0. So this is where, so this is as an element of M to N C, okay, where a hat of x plus iy equal to ax plus iay. That is the only way to extend to the complexification. That's the only way, because it has to be linear, complex linear. So you have to take the I out. That's the only way, and that's what we call it as a hat. Okay, and this will be clear. I don't have to do it. I believe this s minus ij is not symmetric. I mean, its transpose is not itself. But if you take the conjugate, whatever as it is, okay, as a complex matrix, if you take the star, it is self-adjoint. So if you take the inner product, the cross terms will vanish. I mean, if you take what I'm saying is the following. If you take, I mean, these two, the last two equivalent condition can be seen as follows. If you take xy plus I uv, okay, and s hat, s minus ij hat xy plus iuv. Okay. Then you can see that since, I mean, which is going to be s of s minus ij xy and s minus ij uv, and I mean, and the I square will be -1, and since you are taking minus I out, it comes from, I mean, it comes from the first place. I mean, so it's going to be 1. So it is your, since s minus ij satisfies the earlier condition, though only the cross terms you have to look at, but the cross terms will cancel each other because of self-adjointness. Okay, so it's easy to check that. Okay, so let me not write the whole things. Okay, so this equivalence is because s minus ij is self-adjoint. Okay, as a okay.
Self-adjoint and also like it will be conjugate, like conjugately. I'm saying no, antisymmetric.
Yeah, j is antisymmetric.
No, the
So ij
the
is self-adjoint.
like if you let M2n of C, the inner product is antisymmetric, right? That's why it will.
What is that? What is
The inner
antisymmetric?
product on M, like C to the power 2n is antisymmetric.
What do you mean by c to the power 2 antisymmetric? In the first place, it's conjugate linear in one
No, you
variable.
can flip it and like.
Correct. Yeah, it's like that. Yeah.
So
Yeah, you can be, since it's a
yeah,
the same thing. That's what I'm saying. Self-adjointness, we can bring it to the other side, and
then
you are using that. Yeah. So you yeah, that's what I said. Yeah. Okay, it's clear. So proof. So before that, let me state the following, which I stated last time. Let me recall it again, which may be another theorem. Maybe theorem 1. This is theorem 2 on, this is on positive kernel. I mean, it is just a positive kernel. So if this is true for any set, you need not have it on Cn. Okay, if k from x is any set, okay, k x cross x to C, a positive definite kernel. Okay. Let me not say that. No, I don't want to prove it in generality, no. So I take a L. I don't call it. So this is just some function in two variable. Okay. So we can assume it to be continuous, but I think that's not needed. Then the following are equivalent. The following are equivalent. 1. ETL is positive definite. For all t greater than 0. So this is a semi-group. ETL is general semi-group. Okay. It's a semi-group of positive definite functions. Okay. L is conditionally positive definite. I will not prove all the equivalents. I will prove 1 implies 2, 2 implies 3, 3 implies 1. I will not prove. I will orally tell you the proof, not the complete proof, just the sketch. Okay, we don't need that. We only need 1 implies 2 and 2 implies 3. I mean, I have to prove something more for 3 implies 1. So I will not do that. 3 is the function, then this Lxy minus L x naught y minus L x y naught plus L x naught y naught is positive definite for any but fixed x naught in x. Okay. You fix an x naught, then this is positive definite. Okay, this is the theorem. So 3 implies 1, the proof, no, even 2. The 3 implies 1. See, you have to prove that it is something like sum of positive definite. Sum of positive definite is positive definite. That is clear. Okay. Product is also positive. Product of two positive definite functions is positive definite. That is not clear. There is something called Schur product of matrices. Schur product means you know matrix multiplication, which is non-commutative, but there is you can entry wise you can multiply. Okay, that is what is called Schur product. Okay, this positive definiteness is preserved under Schur product. One has to prove it. Okay, that is not clear. One has to prove it. Okay, in KRP book, I think it's in the stochastic calculus. That book, quantum stochastic calculus, in the first section where he discusses positive type definite. It is there. So Schur product, he uses the covariance. He considers any x positive definite. Then it is a covariance of a normal, classical normal random variable. Okay. Then he takes two independent classical normal random variable. Then he takes the product of the Gaussian. Okay. That will be some other. That is also a classical. And that's also a random variable with positive definite kernel xy. With the covariance matrix xy. So he proves it using probability. Okay, that's one way of proving. Okay, so I don't want to go through all that. So, okay, we only need this. We prove this. One implies two, implies three. That is what we will use for the above theorem. Okay, so one implies two. One implies two is direct. Okay, L is nothing but d by dt of ETL at t equals 0, right? Okay. So, but then notice ETL minus 1 divided by t is positive definite. Is that clear? That's because summation, you have to consider summation lambda I bar lambda j, okay, e power t L of xi xj minus 1 divided by t. Okay, and then summation lambda I lambda j bar, there it will be, yeah, it is conditionally positive. Sorry, I'm wrong. E power TL minus 1 by t is conditionally positive definite, not positive definite. Okay. So if summation lambda I equal to 1, I didn't say what is conditionally positive. I said last time. Okay, conditionally positive definite means the following. I don't have space to write. Okay, that is, I'll write it small. That is summation lambda I lambda j bar L of xi xj is greater than 0 for all summation lambda I equal to 0. Even complex numbers, lambda i's are complex numbers. So usually we take general complex numbers. So summation lambda I equal to 0, then this is conditionally positive definite. So if summation lambda I equal to 0, okay, then summation lambda I lambda j e power t xi xj, the first term is positive. Then the second term is just 0. Second term is just equal to summation lambda I lambda j bar e power t L of whatever minus 0, which is just summation lambda I mod square, right? Summation lambda I lambda j, summation over I and j is going to summation lambda I bar times summation lambda I. Okay, so summation lambda I whole square, which is 0 by t. So this is greater than or equal to 0. This is equal to 0 because that is equal to 0. Okay, so this is positive definite.
So how can you say 0 then?
What is 0?
Summation lambda I over lambda j.
Summation lambda I bar lambda j over I and j equal to summation lambda I summation lambda j.
Oh.
So this is equal to summation lambda I whole square mod square. That's all. So over I and j, summation lambda I whole square, mod whole square. Okay. So because of that, that's equal to 0. Okay. The same trick in the inner product. usually like that. So we have only the first term which is greater than or equal to 0. That is positive definite for, I mean, so that term is positive for all t, and positivity is preserved when you take limit. That's all. You have to take the limit t going to 0, right? So limit t going to 0 is positive definite. So this implies summation limit t going to 0, whatever, this greater than or equal to 0, which is equal to L of, I mean, which is equal to summation whatever, that L of xi, xj and all that, which is equal to summation lambda I bar lambda j L of xi, xj. Okay. So that is the limit. So that is greater than or equal to 0. So if e power TL is positive definite, then L is conditionally positive definite. Okay. That's one thing. Then the third condition, 2 implies 3, is direct. For 2 implies 3, I want to prove we have something, some L of xy minus some term. Okay. That is positive definite, we have to prove. Okay. So let lambda 1 up to lambda n, okay, I mean lambda k or something. We want to prove that for general lambda 1 up to lambda k, that summation lambda I bar lambda j, that whatever the function we have, call it k or something, k xi xj is greater than or equal to 0. So I take lambda 0 to be lambda 1 plus up to lambda k. I should take minus. Okay. Then summation j equal to 0 to k. Okay, I include 0 also, lambda I equals 0. Okay. So this implies summation lambda I bar lambda j L of xi xj with k j starting from 0, okay, is greater than or equal to 0. So we just have to keep the other terms and then see what happens for the 0 term. J equal to 1 to k lambda I bar lambda j L of xi xj. Okay, the 0th term, that is going to be, and 0, and I mean take x1 up to xn, x0 up to xn. Okay, these are all in x. Okay. We fix an x0, and all the other x1 up to xk is varying. Okay. Okay. So this is equal to summation this, and here summation. So the first term is lambda 0 times lambda summation j equal to 1 to k lambda j, okay, times L of x0 xj, okay, plus summation j equal to 1 to k lambda 0 lambda j lambda 0 bar lambda j bar lambda 0 L of xj x0, okay, plus summation j equal to 1 to, no, there is no summation, lambda 0 bar lambda naught, okay, times L of x0 x0, right, x0 x0. Okay. Lambda naught 0 lambda 0 naught, that you get mod lambda naught bar lambda naught. No, that's okay. Right now, you will get lambda 0 bar lambda 0. So this is equal to summation. This is that j equal to 1 to k. This is greater than or equal to 0. The first one, this is conditionally passed. That is greater than or equal to 0. So that's okay. This is okay. So this is equal to, I take summation. Let me write it. J equal to 1 to, this is what I want. Lambda I bar lambda j, okay, L of, so whatever that, xi xj plus lambda of, I mean this lambda 0 summation, okay, lambda 1 up to lambda j, so summation, so this is equal to lambda of x0 xj, sorry, this is minus Lambda 0 is minus of the sum, right? So minus L of xj, xi, sorry, xi. Xi, x naught plus L of x naught, x naught. Correct? Is right? Summation j equal to not j, I and j. Both I and j. Okay. And we know that this is greater, this is equal to that. Right? So this is what I have written. See, L of xy minus L of x naught, y naught. The variable, the last one is just constant. Okay. So that is why I get summation lambda I, lambda j bar, just the modulus of that. This is the function kxy equal to this. Okay. Kxy equal to this. This is positive definite. Okay. So this is exactly equal to summation ij lambda I bar lambda j kxi xj. That's all. That is what we have assumed to be.
Okay. Yeah.
It is conditionally positive definite. I take lambda naught equal to minus of summation over that, and the whole thing, the summation is 0. Then I apply the positive definite, conditionally positive definiteness of L, and I get the positive definiteness of this. That's all. Okay.
So in the definition, it should be like L of x comma y minus L of x naught comma y minus L of y comma x naught only.
Y comma x naught, x comma y naught. Oh, sorry.
Because like in
Right.
our
Right. So
The
x comma x naught.
constants are
Yeah. Here x naught. Sorry. Sorry, this would be x naught.
X.
I'm sorry. Yeah. Correct. Yeah, good. Correct. Yeah, it's x naught only. So when we apply, we will take this x naught to be 0. Yeah, it should be x naught in both the places. Correct. So there is no y naught. Sorry, there is no y naught actually. Sorry. Yeah, it should be x naught. Yeah, that's a mistake. Overlooked it. Yeah, now it's fine. Now. Okay, now it's fine. Okay, so this is what we want to apply. So now the proof of theorem 1. So we only have to, so the theorem is, we are given a function, we want to prove that is a characteristic function of a Gaussian state. Okay. The point is, it is enough to prove it's a characteristic function of some state. Okay, and we know then it's a characteristic function of the Gaussian state is clear. Okay, that you can verify. I mean, if you put a t on it, if you fix z and if you insert a tz, then you know that that's a characteristic function of that. That will mean that p of z follows Gaussian. I mean, so okay. So it's enough to prove that it's a characteristic function of some state. So we have a criterion, positive definite criterion for that. We will use that. Right? Right now, we have a criterion, Bochner's theorem, which says when some function is a characteristic function of a state. We prove it's a characteristic function of some state. Then it has to be Gaussian because it is of this particular form. It has to be Gaussian. So we only want. Huh? Yeah, 3 implies 1. I said I will not prove. I was saying because it involves something. I have to prove should product, and I mean we don't need it. We will only use 1 implies 2 and 2 implies 3 for this theorem. Okay, so okay, so we only have to prove it's a characteristic function. Okay, first. F is a characteristic function. Characteristic function of some state. Okay, that's what it means. Okay, so which is equivalent to Bochner's theorem, which is an equivalent condition. Quantum Bochner's theorem, if you want. Q Bochner's theorem. It says that K, X, Y, K, Z, Z1, alpha, beta. Maybe I will use alpha, beta equal to e power I imaginary part of alpha, beta, okay, f of beta minus alpha, okay, is positive definite. Right. So this function is this function on Cn cross Cn. So this is positive definite is what we have to prove. So the imaginary part I will write as alpha j beta using the j operator. So let alpha equal to, so let me write alpha equal to x plus iy and beta equal to u plus iv. Okay. Then this k alpha beta is nothing but e exponential of, and here it's plus, okay, I times inner product of xy j uv, okay, minus half right. It's in an imaginary part of alpha and beta. That's what I have written. In terms of alpha, I have taken x plus iy, beta, I have taken u plus iv, and which I can write it like this using the j operator. Imaginary part is given by this. I mean, imaginary part in the real picture, this is the imaginary part. Minus half into. So this is beta minus alpha. Okay. So beta minus alpha. So u minus x, v minus y, comma, u minus x, v minus y. Okay. Okay. So we want to prove is positive definite. We need to prove this is positive definite. Okay. This is positive definite. We have to prove. Okay. So notice that no, we don't need to prove. We assume that. See, what are we doing? It's a correct. So this is an equivalent condition. I want to write the not to prove. We are finding an equivalent condition. We are assuming it's a characteristic function of a Gaussian state. Then it satisfies this. And if it satisfies this, it will be a Gaussian. Okay, so it's equivalent to that. Okay, this is equivalent to this is positive. This is an equivalent condition. Okay, so which is equivalent to saying, this is equivalence coming. Okay, I need to prove the other way, right? Then no, I'm not proving the other way, right? This is a necessary condition. I'm a bit confused. Wait. If and only if, right? Yeah, so I will need the other way also. Okay, let me prove the other way later. I have to prove 3 implies 1. That's all in the earlier theorem. I thought that's not needed. I mean, because it's an if and only if condition, I have to prove the other way. Okay, so this is equivalent to saying, this is equivalent to first we see that if that is positive definite, of course, then k of root t alpha, root t beta is positive definite. Right? So, I mean, one way is if this is k of root t alpha, root t beta is positive definite, then you just take t equal to 1. That implies that. So for this way, you insert a root t there in the root t in alpha and beta. So that you will get a root t in the whole thing and you get a t, it times that. Okay. And it's clear that is positive definite. When that is positive definite, it's just you can take it as a product and you can use the continuity of that and take the product, or you can, I mean, it's clearly positive. You just write it. You can take, I mean, if you have summation, if you have xi, yi, I mean, if you have z1, zi, zj, then you can multiply by root t, you will get to know, right?
The second one.
No, from, yeah, that implies this so if you can insert a root t alpha, root t beta, that is also positive definite. Okay, that's clear, right? So this is positive definite, but then that is just it. You have some function L. Okay, that is equivalent to saying L of alpha beta equal to whatever I have there, I of that xy j uv minus half that u minus x v minus y s of u minus x v minus y, whatever. This is positive. This is conditionally positive definite. If I prove the 3 implies 1. Okay, this is conditionally positive definite. So now let us use.
How does like k of root t alpha comma root t beta? Oh, you just put one.
Yeah.
That.
The other way is just 1. This way you have to.
No, but how does it imply that it has that form?
Which form?
Like exp of.
No, I'm assuming k is that function.
Okay.
For that function,
okay,
I'm just saying I mean, you insert your root t alpha, root t beta. There is nothing. I mean, right? If you do that works for all alpha, beta, and summation, you can multiply by constant and it will work, right? So that I get a semi group like that. Okay. So this is conditionally positive. Now we have to verify what is this. Okay. Now this is equivalent to saying L of alpha beta minus L of alpha 0 minus L of 0 beta is positive definite. I mean, the 0, 0 is 0, is 0, right? L of that. I mean, if you take alpha and beta both to be 0, then L of 0, 0 is 0. So I'm not writing that. Okay? There is an additional term which I'm not writing. Okay. Okay. So, but this is equivalent to saying I just have to substitute, right? L of alpha beta, so which is I times xy j times uv minus half. I first write the alpha beta, u minus x v minus y s into u minus x v minus y. Okay. Then minus L of alpha 0. So L of alpha 0. So first term is 0. There is nothing, no first term. Only the second term you have to worry. So since there is a minus, I put a plus here. Okay, then so only worry about x. So which is just xy s xy. Right? There is a half xy. Okay, plus half uv s uv. That's all. Okay. Now this is equal to, this is positive definite. Now this is equivalent to saying and we just got it, I think. So xy ij uv. Okay. So I mean, you don't have anything, right? uv minus of uv will get cancelled. Yeah. Yes, uv. Yeah. Those things will cancel and it is only half. There is a half. Is there a half? XY get cancelled and UV, XY. And there are two such terms. So there will be one. Let me write it and then convince you about it. Minus. I mean, S is positive. S is symmetric.
There are so many equivalent conditions.
Huh? What?
There are
No, that is
so
positive, definite. I'm just writing this each statement. There is no equivalent.
Oh,
There is
okay,
only
fine.
one condition. This implies that this is equivalent to this, this is equivalent to this. That's what I'm saying. It's not equivalent condition. We
I
are
thought
proving.
you were like defining many equivalent.
No, we are proving it. Proving the theorem.
I got lost. in the-
No, so what we are doing is we take F.
Yeah.
F is that. We want to prove that is a characteristic function of. I mean, I assume that I mean, we have to prove 3 implies 1 also, if it is equivalent condition. So this F is characteristic function of some state, which is equivalent to saying K alpha beta, this is positive definite. That is equivalent to this is positive definite. That is equivalent to this is conditionally positive definite. That is conditionally positive definite is equivalent to this is positive definite.
Yeah.
I'm just writing it. That's all. I'm just expanding it. That's all.
Yeah.
Okay, I'm just expanding it. Okay. So this is equal to UV SXY. Right? SXY. The last term is because this is positive definite. This function is positive definite. This is a function of two variables. Two variables, xy is one variable, ub is another variable. Okay. This is a function on positive definite on Cn cross Cn. Okay. Where Cn, if it is alpha is equal to x plus iy, I mean, you should remember that alpha equal to x plus iy, beta equal to u plus iv. Yeah.
Yeah, the third condition. Alpha is equal to.
Alpha?
The third condition.
Hmm.
After positive definite.
Correct.
Again, positive definite. How does it imply F is continuous?
No, we are assuming F is continuous. F is given by this exponential function, which is continuous.
What?
Is the
Oh, yeah, F is this, or F is this. Sorry.
EX
I mean, F is given by that.
minus
The theorem is starts here. Our F is a particular F. We have this F, particular F. This F is a characteristic function of something.
Yeah.
Okay, if we are using the Bochner's theorem to get the condition, we are deriving the condition. Okay? F is given by this precisely. Okay, then I am saying that F is, we want to, so I'm just, this is an F is a function given by that. That is a characteristic function of a Gaussian state if and only if this operator is greater than 0. That's what I want to prove. So I assume first, I write the statement. F is a characteristic function of that, which is equivalent to saying this is positive definite by Bochner's theorem. Okay, which is equivalent to this, I have just written using the previous theorem. And finally, I got this. Okay. And maybe you can write that. This is not exactly the same form in the paper, KRP. Because I have, for not to be very messy, he uses, I use the J operator, I have written it in this form. Okay, this is slightly a better form. So finally, what does it mean? This just means this function xy ij minus this, s minus ij, no? How come? You should get x minus ij. Is there a mistake there? Those will get cancelled. Minus half uv minus x minus y. Yeah, this will be plus. Correct. This will be plus. See, uv, the cross terms, uv minus x minus y, and there is a minus outside. Because this will be a plus. And it's a symmetric matrix. So you don't have to, I mean, I'm just computing this inner product, this. Okay. In this inner product, UV inner product SUV will cancel with that. Okay, half of UV inner product SUV will cancel with that. And XY inner product SXY will also cancel. Okay, the cross term only we have to worry. The cross term is UV minus X minus Y. Right, so it will.
UV and SXY and XY and SUV also, right?
Right, huh?
Oh, you're taking it to the other side.
Yeah. Okay, and so yeah, we can take it to the other side because it's a real inner product. So okay, so this is okay. So here we will get plus, and here I am supposed to get minus, but this is linear in the second variable, no? Oh yeah, because x y and I, this is interchange, no? Ij is self-adjoint, so I will get Ij here.
So, but S is just like S is any matrix.
S is
Self-adjoint or is it any?
S is self-adjoint. I mean, S is a positive matrix.
Oh, S is positive. Okay, then because in the statement you just wrote S is in M2 and of R.
Right. We are deriving the condition, no?
Because like otherwise you'll get SUV comma XY and SXY and UV.
Correct.
You'll get
That's what
both
you
of
will
them.
get. Yeah, both of them will get. Yeah, maybe in the. Okay, let's assume S is positive here. Because we know that if it is Gaussian, then that implies S is positive.
Yeah.
I mean, if it is a covariance matrix, it has to positive matrix. Okay. And if it is positive matrix, I mean, if it satisfies this condition, it will be automatically positive. S minus Ij is greater than or equal to 0. Okay. I mean, it's an exercise. You work it out. So the point is, what is Ij? Ij is identity. So in the off diagonal, you have an I times identity. When you have S minus that, it will be, I mean, minus I you will get. So there will be in the off diagonal, and so it will be like this. If S is like this, right? S will look like that. A, B, C transpose, right? This is how S will look like. So S minus Ij will look like plus I here, minus I here. Okay. So that, so that it's symmetric and so that it's self-adjoint. Okay. Now this will only, I mean, this is greater than 0, S minus Ij is greater than 0, will imply S is greater than 0. For example, you compute.
Ij is positive, so S will also be positive, right?
Ij is positive, right? Yeah.
So
Ij is positive.
Should be.
Ij is not positive. Ij is not positive. Because if you take XY, no, Ij, if you take XY, Ij, XY, okay, that is 0. This is what, this is 0 all the time.
Yeah.
No, it is not Ij being added to that. It is just, it will only affect the cross terms. If you compute this S minus Ij, XY, S minus Ij, if you take the inner product, this will be 0. Sorry, this will be 0, equal to 0, not greater than 0. This is equal to 0. Okay. But when you compute S minus Ij, XY, S minus Ij, you will have something like SXY, IJXY. Okay, those terms will be there. Okay, that will only add to something. Okay, you should, I mean, in 2 cross 2, it will be clear. If you take a 2 cross 2 matrix, what will be that? Even, I mean, if you consider the determinant, for example, you will get something like Aij. Okay, you have, I mean, this is just Aij. You have a matrix like this. Then Cij plus I. You will have Cij minus I, and you will have Bij. Okay. If you take the determinant, I mean, so okay, let's just consider 2 cross 2. Okay, if you take the determinant, which will be Aij, Bij, okay, plus, I mean, minus Cij square plus 1. Right? Okay. If that is greater than or equal to 0, then I mean, you can see that that should also be clear. No, minus 1, sorry. I said I wrote plus 1, it's minus 1. Minus 1 is greater than 0, so it should be greater than 1. It's something like Aij, Bij, okay, is plus, I mean, is greater than or equal to 1 plus Cij square, right? Cij square, whatever. So all I'm saying is, if so, we can assume that S is positive. If it satisfies S minus Ij is greater than 0, then it will imply S is positive. On the other hand, if you assume that is a characteristic function of a Gaussian state, that automatically implies S is positive. Okay. We only have to worry about S minus Ij here. Okay. So this is okay. So this is equivalent to this. Okay. Now this is equal to, I didn't write J here. Yes. And then this is UVij. I mean, let me put the I here itself. I, and then have the J here. Okay. But then this is equal to UV. I want to see, that is where I get the minus UV, XY. Right. And now I put the I here. I mean, there is no point in putting, I mean, this is a real inner product, but still I put the I there. Okay. I mean, when you compute it, it will be okay. You can consider only real elements, but assume that they are in Cn or something.
It's conjugate linear in the second.
Yeah, it's linear in the second variable.
Then why do you put minus I there?
That's because I have taken xy juv to be uv jxy.
Oh,
J,
okay, fine.
J transpose is minus J.
Yeah.
Okay, since J transpose, because of that, I'm only using that. J transpose equal to minus J. Okay. XY. Since I have interchanged UV and XY, okay, because that's what I want to get. UV SXY. Okay. So this whole thing is equal to, this is positive definite. This whole thing is equal to UV S minus Ij XY. Okay. Is positive definite. This function is positive definite. Now, if I mean it's clear, no? If this is equivalent to saying XY S minus Ij XY is greater than or equal to 0 for all XY. In order. I mean, this is a general fact. If you take any x ay equal to kxy, this is positive definite if and only if A is a positive definite matrix. The reason is summation lambda I bar lambda j k xi xj is equal to summation lambda I xi, okay, I over I, summation over j lambda j xi a. So this is equal to that. So this kind of function x ay kxy equal to that is positive definite if and only if. So this is positive definite is equivalent to saying x ax is greater than or equal to 0. That's all for all x. Okay. So we got the right condition. Except that I have to prove 3 implies 1. Okay. So shall I prove it now or later? L is conditionally positive definite, then ETL is positive definite. Yeah. So that is needed to prove. Yeah, if if this is S minus Ij is positive definite, then we have to go through all this implication to prove that. Then it is a characteristic function of a Gaussian. So for that we need that. Okay, I will think about it. I will get a, get a reasonable proof, elementary proof, and we'll do that later. Okay. Okay, so we approved it. So let's consider whatever we've gone through. I will just go through that. Now consider n equal to 2. N equal to 1. Okay. Then a matrix S equal to whatever we just saw. I'm just writing it again. CC. Okay. ABCC is a covariance matrix of a Gaussian state on L2R, of course. L2R. If and only if S minus I, this 0, 1, 1, 0. Okay. This is greater than or equal to 0. So which is equal to saying A C minus C plus I. C minus I. So here this minus 1. Okay. And C plus I. No, that is plus. This is minus. That's okay. B is greater than or equal to 0. So this implies this is equivalent to saying AB is greater than or equal to C square plus 1. Okay. So if you assume C equals 0, if C equals 0, this just says AB is greater than or equal to 1. What is A? A is the variance of the position operator. B is the variance of the momentum operator. Okay. The variance of that together should be greater than or equal to 1. So where 1 is the Planck constant for us. Okay. In maths, Planck constant is 1. Okay. Of course, in physics, you have to put a H everywhere. Okay. Planck constant everywhere, and you have to do it. Okay. So this is the actual uncertainty. Okay. The position operator, position and momentum, both you cannot, the variance of both of them you cannot control. Okay. If you decrease the variance of one of them, then the other one will blow up so that the product will be greater than 1. If it is near 0, A is near 0, then B will be near infinity. Okay. I mean, it will blow to infinity. So that's what this says.
So, but like, what if C can be imaginary also, right?
No, C is a real matrix. No, S is a real matrix.
But like covariance between two operators can be imaginary also.
When what do you
C
mean?
is covariance between position and momentum, right?
Right, they are self-adjoint operators. Then that will be real. Covariance is a real, right?
No, if they don't commute, then they can be imaginary. That's what was there in KRP. Like,
No, it is just you take trace of something plus something.
trace of rho times x star y.
X minus, I mean, sometime back we looked at it. X minus the mean, rho into x minus y minus b, the other mean. But you symmetrize it by taking the other one also. Okay.
And I'll check because like when I was reading, he had given covariance of like some two Pauli matrices will be imaginary.
No, covariance is.
I mean, yeah, this kind I'll show you.
See, covariance of xy equal to half of trace of x. I mean, assume that mean of x and y is 0.
Yeah.
Let's assume mean of x and y is 0.
No,
Okay. X row y. Okay. Trace of y row x.
like here, this is written the covariance between the polyspin of the observable sigma 1 and sigma 2 in any state row is I times trace of rho times sigma 3 minus.
But what is his definition of covariance? I mean,
Sure, this one.
hmm. Yeah. So
So it can be imaginary if.
but see, the point is he has written as this is the covariance. No, this is the covariance.
Yeah.
Okay. So he has written x star y. So if you take this definition, it will be.
I mean, if they're self-adjoint, it's same, right? Like x star.
What? Yeah,
Like-
that's okay.
Yeah.
But I have taken it the other one also. I have symmetrized it like
Oh, okay,
that.
fine.
Okay. If you take this,
Fine,
this
okay.
will not be the case. That is what occurs there.
So, what is the correct definition?
It's up to you. Okay. Okay. I mean, there it will mean that the covariance between x and y is not same as covariance between y and x, right? It will be the conjugate of that. It will be conjugate of that.
Yeah.
Okay.
Yeah, exactly.
So, but we assume both are same. Covariance between x and y, covariance between y and x are same. It should be. Okay.
Fine.
Yeah. We take this half times this. Okay. Possibly this is the right definition.
Yeah, like.
Because that's what he mentions in this book, which is written, I mean, this paper, which is written in 2000, that was written in 80s. Okay. There's a 20 years gap. So people come up with the right definition later. I didn't look at it. Yeah. Okay. So this should be the right definition, whatever I have written. Yeah. This is in his paper now, in this paper. Okay. So this should be the right definition. Okay. So good, you have gone through that. Okay. Okay. So we get the uncertainty principle. I mean, the for one variable, I mean, n equal to 1 through this. Okay. So, okay, now by we know that we get all mean by conjugating by the Weyl operators, and by conjugating the symplectic one, we get this L transpose L. We will get. I mean, we get if we get any L we get I mean, if we have L is a symplectic thing, then we get L S is equal to L transpose S. We will get anything with this covariance. Okay, that we can get. And let's see, there are other examples. I don't want to do all that because you can go through and we can discuss it in the exam. Okay. So the about how it behaves with tensor, it's all very easy. Directly, it's all obvious facts. Okay. Immediate facts. So how it behaves with tensor products, how it behaves with marginal trace. Okay. There is only one thing which is non-trivial is which follows immediately when you use all those theorems is purification of a Gaussian state, of not all Gaussian state, some particular form. See, if you have, it is something like this, purification of, if you have some covariance matrix of this form, okay, Li, I think, Li is positive, summation Si Li, okay, if S is equal to this, then you can purify this. You know purification, no? You know, we have seen, you know what is purification is. If you have, see, a state can be given by a vector state. State can be a vector state, or it can be a general operator, trace class operator. Okay. Then you can amplify that into a bigger, I mean, you see, if you have a state on a Hilbert space H1, okay, which is need not be a pure state. Then you have a pure state on H1 tensor H2. Okay, such that if you take the marginal, you will get this state. This is what is called purification. Okay, and that will satisfy that. When we gave an exercise, no, which was a problem in the last year exam, last semester exam. So
What is H2?
some Hilbert space H2. You can amplify that. Amplify H1 by tensoring with some H2, so that you have a pure state in that H1 tensor H2. When you take that, when you trace out, you know, that margin, when you trace it, you will get this state. Okay, so that is what purification is state. Okay. You get a pure state, that's all. Okay, so say all these states can be purified. That is something which is in the, I mean, if you use all this, this is just to have a matrix with row S1 up to Sn, and then you will get, I mean, you take the corresponding symplectic operator and get the You can just read it. It's very easy. So that I will have something to ask in the exam.
We'll have an exam, sir.
We'll have an exam. Small exam.
What about presentation?
When do you want to present? I will stop this.